All right, gang, central limit theorem part 2. I'm going to do more working problems and less talking and teaching here so we can speed this one up just a little bit. So in working with z-scores, whether the z-score formula may be x minus mu over sigma for a single score, or x bar minus mu over the standard error if we're looking at the z-score for a sample mean. Regardless, a z-score greater than positive 2 or less than negative 2 indicates a sample mean that is unusually low. Now, it doesn't only necessarily that the sample mean is unusually low. It could be just a particular measurement, particular point, particular value for x is unusually low. All right, business analysts estimate that the length of time that people work at a job is normally distributed. That surprises me. I would have thought it had been positively skewed. Okay, anyway, mean is 6.2, standard deviation 4.5. What is the probability that a person is selected at random? So a person says n equal 1, so the standard error does not apply. This is what applies for z-scores. Works at the same for more than 10 years. All right, gang, that's an easy problem. So distribution, normal CDF. So what do we have, more than 10? And the mean is 6.2. Standard deviation 4.5. Make sure we have no typos. 1.1992. All right. What's the probability that 12 people are selected at random and their average? So guys, we're dealing up here now. We have the standard error instead of the standard deviation. Average time worked at the same job is more than 10 years. Well, same problem. I can go second function entry, which brings the previous command down. The only thing I need to do is divide by the square root of the sample size, which is 12. Now, sometimes people will say, well, does it matter if the sample size isn't 25 or bigger? It doesn't when you are drawing from a distribution that is claimed to be normally distributed. The sample size of 25 only pops in 25 to 30, depending on the textbook, when you have a distribution, a parent distribution that's positively or negatively skewed. So it just depends on the distribution that you start with. So this is perfectly fine because we have more flexibility because we're dealing with a distribution that's normally distributed. And you'll see that the probability is much less, rounded to 4 places, 0.0017, because the variability in this distribution, 12 at a time, is far less than the distribution 1 at a time. Calculate and interpret the z-score for a person, n equal 1. Same job at 13 years. All right, let's make sure we get this in the calculator correctly. All right, 1.51. So the interpretation of that is we can say that a person who has spent 13 years on the job, the same job, is 1.51 standard deviations above the mean. So a person who's worked 13 years is 1.51 standard deviations above the mean. All right, a random sample of 35 is selected. This is irrelevant. This is what we need. All right, the x bar is 13. The mean is 6.2. Standard deviation we get from the original problem, 4.5. but the sample size is 35. Put the denominator in the numerator in parentheses so you don't get anything crazy. So 13 minus 6.2, same thing we've got. The only difference is we have to adjust the denominator. And we get 8.94. Now back to what we talked about earlier, if it's greater than 2, if the z-score is greater than 2, then it's unusually high. This is unusually high. This one isn't. Why not? Well, to get one person that has a particular measurement that's, quite a bit above the mean with this big a standard deviation, isn't that unusual? But to get something that is this far above the mean in terms of standard errors, it's very unusual. Guys, the standard error here is 4.5 divided by the square root of 35. 0.76. Starting at 6.2, how far do you have to go up by 0.36 to get to 13? Well, 8.94 of them. How far do you have to go up from 13? Let's see, I'm sorry. How far do you have to go up from 6.2 to get to 13 when your standard deviation, you're going in 4.5 chunks? Well, only 1.5. Okay? So it's the difference in the mean based on standard deviations or standard errors. All right, gestation periods are normally distributed with mean 266 standard deviation 16 days. What's the minimum gestation period that places a woman in the longest 10% of pregnancies? Well, if we're in the longest 10% of pregnancies, that means that we're up here, because as we get further to the right, we get into bigger numbers, which in this context of this problem is, well, it takes longer, okay? So we want to find the value right here with a mean of 266, standard deviation of 16, that has 90% below it. Well, guys, the key that we're going to use there, we haven't used it in a while, is inverse norm. And remember, inverse norm works with what? Percent below. Standard deviation, or I'm sorry, the mean, standard deviation. So this, the one gestation period that would place a woman's n equal 1, so we don't get into any of that fancy smancy stuff with the central limit theorem. One woman. Do stuff like we did the last 2 or 3 weeks. So the gestation period would be 286.5 days. All right. Now we got a group of 10 women. So instead of one woman, we got 10 women. So our focus is on a sample mean. And when our focus is on a sample mean, we focus on the standard error instead of the standard deviation. So same problem. What is the minimum average gestation period? So it's the minimum average, not the minimum gestation period for one person. It's the minimum gestation period for 10 people, 10 women taken at a time. Longest 10%. Guys, works the same way. But because this distribution is taller and skinnier, this is going to be what? Which way? To the left or to the right? Well, it should be pretty clear, but let's just let the calculations play their way out. So 10%, so that tells me I got 90% below. So the calculation is exactly the same as before, except what? You got to divide out by the square root of the sample size. Now, is there any issue? So it's going to be 272.5. is the X bar of the 10 women that would put their average gestation period in the top 10%. All right. Now, it should have been clear this was below because of the fact that our distribution squeezes in, the variability becomes less. So we knew that this was going to be closer to the mean to achieve the same proportion of the distribution. Okay, number 3, the weight of potato chips is stated to be 10 ounces. It never is. This is within some degree of measurement tolerance or some degree of measurement error and measurement accuracy as much as anything. The amount that the packing machine puts into these bags is believed to be normally distributed with a mean of 10.2 ounces and a standard deviation of 0.12 ounces. Guys, when I was going to college, when I was an undergrad, I worked for a produce, and what the FDA, Food and Drug Administration, takes this stuff really seriously. So if you say that, for example, a steak is, I don't know, let's just say 2 pounds. They take that seriously. They really want that steak to be 2 pounds. If it's bigger than 2 pounds and you get charged for 2 pounds, then they're okay with it. But if that steak is actually 1.8 pounds and you charge for 2 pounds, then the owner of the grocery store can get into a lot of trouble. I saw it happen firsthand. I had nothing to do with it. I just witnessed it. So anyway, what they do typically is when they create the filling machine, as in this situation right here, and they say that the amount of potato chips is 10 ounces, they set the average at 10.2, so they're assured that less than half of their potato chips are going to be less than the stated amount. So we're going to get into an examination of that here, okay? So what percent of bags sold are underweight? Now typically the FDA will allow 5% measurement. They will allow 5% to be underweight. Again, they don't care if you pay for 10 and get 20. They don't care if you pay for 10 and get 10.1. They may not even care if you pay for 10 and get 9.9 based on the standard deviation. But if you get too far below the stated amount, then you're not getting what you paid for, and the FDA loses their mind over that. So what percent are sold are underweight? So to be underweight, we have a distribution of mean of 10.2 and a standard deviation of 0.12. Well, to be underweight, we need to be 10 or less. Okay, so that's going to be a very easy problem. Normal CDF, negative E99, comma 10, comma 10.2, comma 0.1, shoot. There we go. All right, good. So here you've got about, multiply by 100 to convert it to a percentage, so we have about 4.8% of the bags sold underweight. Now, FDA will be okay with that. If this gets bigger than 5%, it's my understanding that they can levy some fines. Now, some of the chips are sold in bargain packs. Now, when you get into bargain packs, they stop focusing on the particular measurement of a bag, and they look at the average weight of the 3 bags. Okay? So as long as the average weight of the 3 bags is not less than the advertised amount, then they seem to be okay. So what is the probability is under the stated amount? Okay, so what's it under 10 ounces? Well, it's going to be a lot less because of that whole variability thing. And what I can do is I can go entry, again, And you can see all I need to do now is come in and divide by the square root of 3. Very, very, very unlikely. Convert it to a percentage. So only 0.19%. Now, this is 0.048. This is 0.0019. In case your percentages and decimals, you're lacking just a little bit. That's a tremendous difference. So the company has a lot less concern with selling the average of 3 bags to be underweight than they do to sell one particular bag underweight. You ever see those big 12 packs and 20 packs and why they're so much cheaper? Yeah, may tell you something. All right, what's the probability the mean weight of a 24 bag case of potato chips is below? Well, gang, I need the same thing, so I'll just go second function entry. Put a 24 there instead, and the calculator just tells you it's not going to happen. Now, guys, that doesn't mean that the probability is 0. That's not what that means. It just means that the probability is so low based on the rounding tolerances that the calculator sets up. The probability is so small that I went ahead and just rounded it to 0. And I forget how far that goes out. I think somebody told me one time it goes out to, well, I don't even remember. I used to remember that, but that part of my brain has been replaced by other stuff. All right, gang, that's it. Take care.